All right, next up in our graph theory topics is this idea of coloring a graph. And this topic has a surprising number of applications that many of which don't necessarily seem like they're graph theory questions. The first we'll talk about is this idea of coloring a map. So let's say that we are map makers and we have this blank copy of a map of the continental United States. So if we want to give this color, if we want to label each of the states, we could start off, let's say, with Colorado, and we could give it a certain color. So I am arbitrarily choosing to label Colorado blue, and if I moved over to a state that was next to it, like Utah, and I also labeled that blue, this doesn't look very good, right? Sort of the point of adding colors to maps is to make a distinction between states that are adjacent to each other. So if they share a border, maybe we don't want them having the same color. So let's choose a different color. Let's maybe label Utah with yellow and go from there. So if we look at another state, let's say Wyoming, which is this one, we don't necessarily want to label it blue because, well, then we have that border issue with Colorado. We don't want to label it yellow because then we have a border issue with Utah. So really we sort of need a new color. So let's label this one orange and continue on our way. So one thing that is allowed is that if we have states that are pretty far apart, we're certainly allowed to reuse a color. If we're labeling all 50 states and if we needed different colors for each state, we need a ton of different colors. And maybe that's annoying for us map makers. So for this, typically the goal is to try to use as few colors as possible. All right. One other caveat is that if we have states or regions in our map that are only next to each other or only adjacent at a single point, then that doesn't really count. If we wanted to label both Utah and New Mexico yellow, that would be allowed under our rules that we are somewhat arbitrarily deciding. So we could continue this process, and maybe along the way there is some arrangement of states or regions that forces us to use a new color, maybe a fourth color. And we could conceive of a situation where, hey, maybe we then need a fifth or a sixth. So one question that we have is, given a map, how many colors do we need? And maps are somewhat inherently complicated objects to work with. So to answer this question, we'll convert the question to a question about graphs. So here we'll take what's called the dual, which is a way of translating a picture like a blank map into a graph that encodes the information that's important. Right? We don't really care what the shape of Texas's coastline or border looks like. All we really care about is which states does it border. So to encode this information, we'll give every state a vertex, and we will say that two vertices are adjacent, right? There is an edge connecting two vertices when their corresponding states share a border. So we can include these edges because the vertices on the endpoints of the edges correspond to states that share a border. We would not, for example, draw an edge between the Nevada point, the Nevada vertex, and the Colorado vertex because there is no border between those. We would not draw an edge between Utah and New Mexico because a single point doesn't count as a border. However, we want to draw all of the other edges that we possibly can. So when you're done, you might have something that looks like this, but the whole point of using this graph rather than a map is to be able to get rid of all the information about the map, and we're left with just a graph. And now we can ask all of these same coloring questions about the graph itself. We'll say that a coloring of a graph is an assignment of a label, so think of this as a color, to each of the vertices of a graph. So if we have a graph like this one here, we can start coloring it by labeling each vertex with a color, with a label, and as long as we follow the rule that if we have two adjacent vertices, they have different colors, we can generate a coloring. And so we can use however many different colors we want, but typically what we're interested in is the chromatic number. So the goal is typically to use as few colors as possible. So here is a graph G that I've drawn using only 3 colors. So if we can show that it's not possible to color this graph with only 2 colors, then we will have shown that the chromatic number, gamma of G, is equal to 3. Now, one word of warning here, many books and other sources and articles, rather than using gamma to mean chromatic number, they use chi, which I think is terrible because we also use chi to talk about the Euler characteristic, and a lot of places just use it to mean both. So to avoid confusion, we are giving it a different name. We are calling it gamma and going from there. But just so you know, other notations are out there. We can use graphs and coloring of graphs to model situations where what we want to keep track of are instances that don't play well with each other. So say we have 2 chemicals that can't be stored next to each other, or maybe we are working with scheduling and we can't have 2 activities happen at the same time. Well, we can model situations like this using our vertices to represent the objects and connections or edges when these objects can't both be the same label. We'll see an application like this or two on the homework, but for the most part, that's all I have to say today. So moving forward, many of these questions are ideas that I want you to think about for yourself, to work through as a group. This video is really just laying the groundwork, and there will be plenty more follow-up in class on Friday, and then we will be talking more about coloring on Monday as well.